we really need to talk about AI's most expensive habit. I'm talking about its addiction to scale.
The brute force approach.
Exactly. For the past few years, the whole community has been running on this one simple law. If you want a smarter answer, just build a bigger model.
A more generalized model, yeah.
So now we have these massive monolithic things, these frontier models. They're like digital deities.
Yeah.
And we ask them to do everything from, PhD level physics problems to just writing a 2-line Python script.
And that's just not sustainable, is it? Operationally, it's a disaster. That's where all the inefficiency, the cost explosion really comes from.
It feels like hiring a Nobel Prize winner to calculate your grocery bill.
That's a perfect analogy. They'll get it right, of course. They'll give you the correct answer. But you're just wasting so much capacity and so much of your budget. And I think that realization is forcing this huge architectural pivot in the industry.
It is. And the source material we're looking at today shows this shift isn't just a theory anymore. It's actually being executed. We're talking about a new architecture from NVIDIA called ToolOrchestra.
Right. And the core model inside it, this Orchestrator 8B.
An 8 billion parameter model.
Yeah.
Which sounds almost small now.
It does. And what's so startling is how it directly challenges that whole bigger is better paradigm. I mean, here you have a tiny model, relatively speaking, that claims it can beat the huge proprietary ones like a GPT-5.
And not just on any test, but on one of the most rigorous exams out there, the humanities last exam, the HLE.
And it does it while being, what, 2.5 times more efficient? It's a major claim.
So our task in this analysis is to really unpack the blueprint for this new smart manager era of AI. Because this isn't just some small update. It's a total reorganization of how we think about intelligence. We need to figure out the mechanics of how this little manager can outperform the biggest genius in the room.
Consistently and cost-effectively. That's the key.
Okay, so let's start with that foundational shift, from the monolith to the manager. When we look at ToolOrchestra, what's the first mental switch you have to make?
You have to stop thinking of the core model, that 8B model, as the source of truth. It's not the library. It's more like the prefrontal cortex. It's the decision maker, the router.
I like that. So it's not the one with all the knowledge.
No. The whole ToolOrchestra approach is about training that small model, the Orchestrator 8B, to just manage a toolkit. And that toolkit can have all sorts of specialized things in it, a database query tool, a search engine, or, and this is critical, other smaller specialized AI models.
Okay, so I ask it a really complex math problem.
The Orchestrator doesn't even try to solve it. It doesn't have all those formulas memorized in its small parameter space. It immediately recognizes it's a math problem and routes the request to an expert, maybe something like Quen 2.5 math, which does nothing but math.
So the Orchestrator just needs to know who to ask. It doesn't need the answer, just the contact list.
Precisely. That's the huge architectural win here. You are decoupling reasoning from knowledge retrieval. You offload the expensive job of memorizing the entire world onto these cheap, specialized tools.
And that gives you the agility and the efficiency.
Right. And the whole thing runs on this this deceptively simple loop. It's a multi-turn reasoning loop that creates what you could call a composite intelligence.
Okay, so walk me through that loop. A request comes in. What are the 4 stages it goes through?
So first, the Orchestrator does reasoning. It looks at the input, checks the state of the problem, and thinks, okay, what's my next move?
Step 1.
Step 2 is tool calling. Based on that thought, it picks the best specialist from its toolkit. Then step 3 is observation. It gets the result back from that tool and reads the output.
And finally?
It repeats. It goes right back to reasoning. Okay, based on that new information, what's my next move? And it just keeps iterating, reasoning, calling, observing, until the whole task is done. It's classic management just for AI.
That structure sounds elegant, but I know previous attempts at this. Well, they've run into problems, like internal politics almost, a bias problem.
They absolutely have. You can't just tell a big model to be a router and expect it to work. The source material highlights this. They call it self-enhancement bias.
Self-enhancement bias. Meaning what?
Meaning, when they tried this with a big model like GPT-5, it showed this really strong preference for calling other models from its own family, like GPT-5 Mini. Even when they weren't the best tool for the job, it was basically AI nepotism.
Huh. And what about the other way around? Using a small router?
A confidence issue. The little model would get a hard question and just punt it straight to the biggest model available every single time, which, completely defeats the point of being efficient.
So the real challenge isn't just teaching it the rules, it's training out that bias. How did NVIDIA get an orchestrator to be so, as the paper says, brutally efficient?
Reinforcement learning. They used a specific algorithm called Group Relative Policy Optimization, or GRPO. The big light bulb moment was realizing you can't just reward the model for being right
You have to reward it for being efficient.
and fiscally responsible.
Okay.
That led them to the real engine of this whole system, the triple reward function.
Okay, this sounds like the game changer. The incentive structure. Let's break those 3 rewards down.
For sure. The first one is the most obvious. It's the outcome reward. It's just a simple binary. Did you solve the problem? Pass or fail. The model has to get the right answer, period.
Simple enough. But the second one, that's where the real behavioral engineering happens, right?
Absolutely. The second is the efficiency reward.
Yeah.
This is the one that directly penalizes the model for spending too much money or taking too much time.
So it learns that calling an expensive API has a cost.
A very real cost.
Yeah.
Through trial and error, it figures out that if a task can be done with a free local Python script, choosing that gets a way higher reward than, say, spending a nickel to call Claude Opus. It is actively trained to be frugal.
I see. That makes total sense for any real-world deployment. But what if there's a conflict? What if the fastest answer is also the most expensive one? How does it choose?
And that's where the third reward comes in, the preference reward. This one aligns the model's strategy with what the user actually wants.
So it listens to constraints.
Exactly. If you tell it, I need this answer in under 500 milliseconds, I don't care about the cost, it will prioritize speed. But if you say, look, I need this cheap, I can wait a few seconds, the orchestrator literally changes its policy on the fly to favor the cheaper tools. It's incredibly adaptive.
That flexibility is something the big monolithic models just can't do, can they? They just run at max power no matter what.
They are essentially deaf to the budget. This proves you can engineer fiscal responsibility right into the agent's core logic.
Okay, so let's get to the proof. Does this complex incentive structure actually work? We have to talk about the humanities last exam, the HLE.
Right. And you have to understand, this is not some trivia quiz. It's a benchmark made of PhD-level questions. It's specifically designed to stop models from just succeeding by memorizing facts.
Yeah.
It tests real reasoning.
And the results. What's the hard data?
This is where it gets wild. On the HLE benchmark, the tiny Orchestrator 8B system scored 37.1%.
37.1.
Okay.
And the monolithic GPT-5.
Scored 35.1%, a
Yeah.
full 2 percentage points behind.
Wow, so the little manager actually beat the heavyweight? That's not a small difference on a test that hard.
It's a massive validation, and that's before you even think about the efficiency. It got that 2-point lead while being 2.5 times more efficient in tokens processed and costing only 30% of the monolithic approach.
That's the empirical proof right there. A well-managed team of specialists beats the lone genius.
And it wasn't a one-off. The data shows it won across other benchmarks, too. On frames, which is all about factual accuracy and multi-step reasoning, it got 76.3% to GPT-5's 74.0%.
And what about TalBench? That one's specifically for tool use, isn't it?
Yeah. It is. It targets advanced function calling, API management. And there, the orchestrator won again, 80.2% versus 77.7%.
That TalBench result is really telling. It suggests the model isn't just good at reasoning, it's mastering the actual mechanics of using tools, which is what you need in the real world.
Exactly. This is what shifts the conversation from pure research to operational economics. In a world where margins matter, which approach do you choose?
Well, the numbers are pretty clear. The monolith is what, 3.3 times the cost and 2.5 times the latency?
Roughly, yes. The orchestrator architecture is the efficient frontier. You're getting higher accuracy for a fraction of the resources.
And the enterprise relevance is just huge. The orchestrator listens when you say be cheap. The legacy models, they just ignore those constraints and run hot, making them basically unusable for anything high volume.
They can't adapt. Their behavior is fixed.
Okay, let's shift gears a bit. You can't train a manager this good without great training data. And since this kind of data is really scarce, NVIDIA had to just make it. Let's talk about the ToolScale pipeline.
The ToolScale Dataset is the blueprint, yeah. And its genius is the focus on what they call executable reality. They weren't just generating, hypothetical chats about what a tool might do.
No, they built entire simulated worlds, right?
Yeah.
So what are the steps in that synthesis process?
There are 3 main steps. First is environment generation. They'd simulate a realistic domain like creating the database schemas and API specs for a flight booking system.
So they build the playground first.
Exactly. Then comes task generation. This step produced the user questions like, book me a flight to JFK, and also the golden or correct sequence of function calls needed to actually do it.
But the last step, the verification, that feels like the most important part. That's what makes it robust.
It is absolutely the key. The verification step meant they actually executed those function calls against the simulated world.
And if it failed?
If the code threw an error or the database didn't update correctly, that entire training example was thrown out. It was invalid.
I love that. So the model learns from verifiable ground truth. It learns that calling refund ticket with an ID that doesn't exist actually fails.
It learns the mechanics, not just the syntax. That's the difference between a system that works and one that just hallucinates valid-looking JSON.
That grounding is everything. So for people looking to actually deploy this, what's the feasibility? An 8B model sounds manageable.
It is. The inference requirements are surprisingly reasonable. While they used H100s for the training, of course, the final 8B core model can run on high-end consumer hardware. Think an RTX 3090 or a 4090.
That's incredibly accessible.
It is. But the real win for developers is the modularity.
Right. You can swap out the tools.
Precisely. If a better math model comes out tomorrow, say DeepSeek Math, you just swap it in. You update the tool definition. You don't have to retrain the whole orchestrator.
Because the manager already knows how to manage a math expert. Doesn't care which one it is.
It adapts instantly. It makes maintenance and upgrading so much simpler.
Now, the results are obviously transformative, but we have to be critical. This isn't a solved problem, is it? We are still comparing two imperfect systems.
Oh, not at all solved. The biggest critique is just looking at the absolute score. A 37% on the HLE is a huge milestone, but it also means the AI is still failing 2/3 of the time on these really complex tasks.
So we're a long, long way from AGI.
A very long way.
And what about the latency? I mean, orchestration means more network requests, right?
Yeah.
A call, oh wait, another call. Doesn't that HTTP overhead risk making the whole thing feel slow?
That's a valid engineering question, but the data suggests the trade-off is worth it. Because the little specialized models are so much faster at their specific tasks, the total wall clock time is actually lower.
So the speed of the specialists outweighs the network lag.
Yes, that 2.5x speed up they measured confirms it. The gain from focused, rapid computation is bigger than the penalty from the network calls.
Good clarification.
Right.
And last question here. What about generalization? Can it handle really long, complex tasks without forgetting what it's doing?
The initial signs are very promising. The paper says it generalizes well to tools it's never seen before, which means it learned the logic of being a manager, not just how to use a few specific APIs.
And the length.
They trained it on trajectories up to 50 turns long, 50 decision steps. That suggests it's pretty robust against the kind of multi-turn complexity that would normally make a small model just fall over halfway through.
So if we synthesize all this, ToolOrchestra is basically a definitive signal. The era of one model to rule them all is, well, it's ending.
It's giving way to the era of the compound AI system. It's confirmation that intelligence is a discipline you can train and optimize. NVIDIA has given us a blueprint that proves you don't need a trillion parameters, you just need better management.
Better management, efficient routing, and a reward function that is just ruthlessly focused on efficiency.
Yes. A small, smart manager coordinating specialized workers. That's how you build systems that are smarter, faster, and dramatically cheaper.
So if you're an agent developer or you're trying to improve your own company's systems, the message is clear. Stop trying to make your one big model do every little thing. Look at this modular blueprint. This is how you win.
And here's the final thought I'll leave you with to connect this research to your own work. The real test of this architecture isn't the HLE score.
What is it then?
The real test, in practice, is whether the model can figure out how to use your company's own custom internal API, a tool it has never, ever seen before, without you having to fine-tune it on all the documentation.
The logic of management has to generalize to completely new tools.
That's the prize. That's what successful LLM orchestration looks like in the real world.
The ability to adapt and manage unseen resources, that's the challenge ahead. We've explored the architecture for the smart manager era. Now you have to think about how you'll assemble and manage your own specialized team.